Hi everyone, welcome back to this session. This is Jun Rao from Confluent. In this module, we're going to talk about transactions in Apache Kafka. Well, first of all, why do we need transactions? Well, people may be familiar with transactions in the database world. So if you, typically in the database world, if you want to write to multiple tables, having transactions give you the ability to achieve this all or nothing behavior. So either have the rights to all the tables succeed or none of them succeed. Well, we probably need the same thing in the Kafka land as well. So let's take a look at this example. For example, let's say you have this conceived application called the transfer fund. So the input would be this transfer table which recorded the intention of transferring money from one person to another. In this case, Alice to Bob. What we want to do in this application is to take this event, right, which include the transfer, and we'll add two output records into the output topic. We're going to add debit event for Alice, and we want to add credit event for Bob, and that completes the transaction. Once this is done, we'll be committing the input offsets by advancing the offset for the input topic, and this will translate to a write into the internal consumer offset topic, as we mentioned earlier. So for a lot of applications, it'll be nice to have all those three writes, right, for the two output topics and then this internal topic to be done in an all or nothing way. So that will make the developing of the application easier to understand. That's exactly what Kafka transaction provides. It's a feature that allows this kind of application to do the processing and the write to the output topic once and only once, even when the application can fail and get restarted in the middle. Before I talk about the details of transactions, enabling transaction is pretty easy in Kafka. Typically, the way you do that is to enable this through a Kafka Stream application. So there's only one configuration you need to set in the Kafka Stream configuration, which is processing guarantee to exactly once, and we have a version 2 now for some of the performance improvement. Then if you produced some output in this transactional application to read that output topic, you can set the isolation to be read committed, then only the committed data will be exposed to this reader. Now, let's first look at some of the issues without transaction. Let's still continue with that example where you read the input from intention topic, and then you try to add some of the credit events and the debit event, right, to an output topic. Let's say you finish reading the input event, and then you wrote the first debit event for Alice. Now, let's say at exactly this point, the application failed. Now, what do you do in this case? Well, typically, when it fails, you just restart the application, right? And the application will resume from where it's left off. Since previously, we didn't really finish processing the first event, so we didn't really commit offset in the consumer offset topic. So when this application is restarted, it will pick up this event again. And it will try to do the same steps as it did before, try to add a debit event for Alice and add a credit event for Bob. And eventually, it will commit the offset into this commit offset topic. Now the application steps is done. But notice that now if you have application reading this output topic, it will see the account for Alice is debited twice. This is actually annoying because it's very hard for application to reason about this and deal with it. Okay, now let's take a look of how this issue is solved with Kafka transactions. If you have configured, let's say this is a streaming application with exactly one semantic, then the stream processing will automatically set an internal configuration called transactional ID to uniquely identify this particular application. When this application is started, the first thing it will do is to find a transactional coordinator to coordinate for this transaction. Now, how is the coordinator determined? It's actually determined in the same way as we had for the consumer coordinator, if you remember it. So what's happening is there's an internal topic we use for storing all the transactional related information. It has multiple partitions, and the leader of the partition this transactional ID hashes into is the transactional coordinator for this application. Once the coordinator is determined, then the coordinator can generate a unique producer ID for this transactional application and a corresponding epoch, and will send this information back to the application. The next thing the application will do is start reading from the input event, and then it's about to write the output. But before it writes that, it needs to inform the coordinator that it intends to update or write to an output topic. So it sends this information to the coordinator, and the coordinator will persist the partition that will be part of this transaction into this internal topic. Once this is recorded, then the application can start writing the event to the output topic. Notice at this point, even though we have written this debited event for Alice, but the data hasn't been exposed to the consumer yet because it's still in this pending state. Let's say now at the exactly same point, the application failed and is restarted. So when the application is restarted, it will do exactly the same thing as it did before. The first thing is it will try to request a producer ID through the transactional coordinator. The coordinator will notice that it actually already knows there's a pending transaction for the previous instance of this application. And then since this one is trying to register a producer ID again, it must be a new instance of this particular application. So what a transactional coordinator will do first is try to abort all the pending transactions from the previous instance of this application. It does that by adding a abort marker to the internal transactional log, and it will also add an abort marker to each of the partition this transaction has written data into. In this case, it's just this particular partition. Once this is done, the transactional coordinator will bump up the epoch for this producer ID. This will be used to fence off the old instance of this application. So in case this application didn't really die completely and mysteriously come back, it cannot do any null writes for the new transaction because it will notice that its epoch is too old compared with the latest epoch associated with this application. So after all this is done, if now you can see if the consumer is trying to read this output topic, it actually will ignore this debit event because it's marked as aborted and shouldn't be exposed to the application. At this point, we have avoided this issue of exposing aborted data to the application. Now, let's look at what happens to a successful transaction. So you go through pretty much the same steps as before. When the application started, it first requests producer ID from the transaction coordinator. Then it will read the input, but before it writes to the output topic, it will send the coordinator the set of partitions that they need to add data into. In this case, there will be 3 partitions, these 2 partitions and an internal partition for the offset topic. The coordinator will record all those partitions in the transactional log. After that, the application can start writing the new records, those 3 output topics, including the offsets. Once this is done, the application can send a commit request to the transactional coordinator, and the transaction coordinator will write the commit marker within its internal commit log, within the internal transaction log. At that point, that decision is made and can't be changed. After that, it will be adding the same committed marker to each of the output topic based on the information it has recorded. At this point, all the committed information will be exposed to the consumer application if they are reading in this read committed mode. So let's take a detailed look how we expose transactional data for consumers with this read committed mode. In general, we still want to expose records in offset order. But notice that at this point, the high watermark is before offset 66. But record whose offset is at 64 is actually not committed yet because there's no commit or abort marker for this particular transaction. So its state is pending. So in this case, we don't want to expose this data to the consumer yet. So what the broker does is to maintain a new position called last stable offset. This is the offset of all the first open pending transaction. All the records whose offset is before this mark, their state has been determined, which means they are either aborted and or committed, and they can be exposed to the consumers, and we can return those. Another thing that's a bit tricky is if we are returning, let's say, the first 3 records in this picture back to the consumer, some of the records, like the record at offset 57, is aborted, and the consumer should ignore it. So what we do is when the broker sends these records back to the consumer, it also returns a little bit of metadata so that the consumer application can ignore the aborted records like this. So since in general abortion is like relatively rare, there's actually very little overhead to the application. Earlier we talked about producer can enable idempotency to avoid issues of introducing duplicates or out of ordering when the application fails. So if your application is set with exactly one semantic, idempotency is automatically enabled. So in this case, let's say if you are sending some of the events, right, to the leader, the first thing you will do is you will get your producer ID back, and then as you are sending the events, each of the records will be tagged with the corresponding producer ID and a sequence ID. And the broker will be storing those records with those producer ID and sequence ID, and remember what's the last sequence ID it has seen for a particular producer ID. Now, if the leader fails in the middle, then when the producer tries to send new data to the same data to the new leader, the new leader will notice that some of the records are really duplicated and they can ignore those. So by enabling exactly once capability in the streaming application, we automatically enabled idempotency, and together they can guarantee this exact once semantic for the processing of the data. Now let's talk about some of the considerations with transaction. One of the things with transaction is you have to decide how often you want to commit those transactions. There's some trade-off there. Earlier you have seen that there's a little bit of overhead to set up with the coordinator every time when you try to send the very first record to a particular partition. If you are committing only like 1 record per transaction, then that overhead could be significant. On the other hand, if you are including too many records within a transaction, that tend to delay the exposing of the data to the downstream applications. So you want to balance the two. By default, the commit interval is set to be 100 milliseconds, but you may want to tune that based on the application and the performance you want to have. The last thing I want to talk about is a little bit caveat of using transaction. So far, all we have to talk about transaction only covers the interactions within the land of Kafka. But sometimes you may want to do some processing, generate some output, and eventually you want that output to be exposed to some external systems, maybe like an external database. Now, how do you coordinate between these two separate systems? In Kafka, we don't really support two-phase commit. So the transactional support we have is only within Kafka. So to support interaction with two systems, the typical way you do that is to turn that into 2 separate single transactions. You will first design your application so that you can generate output in the transactional application within Kafka. And you want to design it such that the transactional output can be idempotent. Then you will read this output and then write the data records from this output into the external system like a database. If the output of the topic is idempotent, then you can apply the same changes potentially more than once to the external database, but you will get the same effect. So that way, you can bridge the two systems better without introducing too much overhead, like the two-phase commit would do. And that's it for this module. Thanks for listening.